Hi everyone. So today I'm gonna talk about Gromov-Witten theory from string theory, which is a method to solve some problems in enumerative geometry. So the outline of this talk is as follows. First, we're gonna give a introduction and a motivation for this from physics point of view. Then I will discuss the path integral formalism so people from mathematics can understand a little bit what is going on in physics. Also, we are going to discuss why we want Calabi-Yauss in our theories. Then we are going to discuss model spaces and some examples. And at the end, we are going to define Gromov-Witten classes, Gromov-Witten theory, and maybe some examples if there is time for them to cover. At any point, if you have any question, you can ask me. Feel free to raise your hand and ask me questions. Okay, so I want to mention, first of all, some references that I use. The main three references that I use are these three. So if you are, because in this talk, there's going to be math students and physics students. So if you are a math students, you are more interested in math approach or to understand the math of Gromov-Witten theory, then I recommend you the first book. Yeah, it's really well written by David Cox and Sheldon Katz. But if you are a physics student and then you want to understand the physics and the motivation for all this, then I recommend you the second, which treat in really well detailed every aspect of mirror symmetry and also within theory. It has a really amazing authors. Also, a really nice set of lectures that you can find on YouTube or in Binsa is Shesmani lectures on Donaldson-Thomas and Gromov-Witten theory. So he started by Gromov-Witten theory, and then at the end of the lecture, he introduced and explained on Donaldson theories. So yeah, there are also other really nice introductions. If you are not so familiar with this, but you have a really easy introduction, then I recommend you this popular science book, which is by Sheldon Katz, Enumerative Geometry and String Theory. Okay, so our motivation. So maybe you are familiar with quantum mechanics, and then you know if you want to know the path from a particle to go from point A to point B, then this will be given by the equation of motion. And the equation of motion is finite from the Euler-Lagrange equation, which are given from the Lagrangian. So once you define the Lagrangian, it will tell you the path from point A to point B. In Euclidean space or Minkowski space, it's fine. Then in quantum field theory, you you unify classical mechanics and quantum mechanics with special relativity. And then, for example, here, if you want the probability of a particle for going from one point to another, and then you have some interaction, then this will be given by a Feynman path integral. Yes. So the basic idea of the Feynman path integral is if you have a particle A to a particle B, then you will have several paths. And all these paths will be weighted by some probability, and this is given by the action. The action is in terms of the Lagrangian for those who want classical mechanics, but maybe we will discuss this better in the path integral formulation section. And then we integrate over all the possible paths, right? And all these possible paths are gonna be explained by the model space that I call here gamma. In order to integrate this gamma, then in order to integrate all these paths, then it should be compact. Otherwise, you will have an infinite sum. And even if it's compact, then you can have an infinite sum. We will see this later on. Okay, so in the string theory, Now we have classical mechanics inside quantum mechanics, and then quantum mechanics with a special relativity give you quantum field theory. But now we want to unify quantum mechanics with general relativity, which is a quantum theory of gravity. And then the only theory that is kind of successful in describing quantum gravity is string theory. So string theory, instead of having point particles, it has strings. So in this case, when you have a point particle going from A to B, this path will be a straight line because a point just trace a straight line, right? But if this is a string, let's say here, then the path, the trace, when it goes from one point to another, is a surface. It's not a line anymore. So it's a two-dimensional surface. So how can we define a superstring? So superstring is a theory of bosons and fermions that has a supersymmetric symmetry. And then this theory has sense in 10 dimensions. So string theory predicts 10 dimensions. It says in order to make sense, it has to be, the universe has to be 10 dimensions. But we only observe 4 dimensions. So what happens with the other 6? So the basic idea is, let's suppose this plane that you see here is a 4-dimensional pseudo-Riemann surfaces, which means it's Minkowski. It's like 1 time dimension and 3 space dimension. So in total is a 4-dimensional space-time. Then in each point of this surface, this 4-dimensional space, you will put fibers and each point, fibers. And each of these fibers are gonna be a 6-dimensional manifold. We will explain later why this manifold is actually a Calabi-Yau, and this is what is called our ambient space. Our ambient space will be a Calabi-Yau threefold. 3 because it has real 6 real dimensions, but in complex manifolds, then you describe it as a 3-dimensional manifold. So it's a Calabi-Yau threefold. Okay, so the way that you do this vibration is that to every point of the space-time, then you put a Calabi-Yau. And we say, or we argue, that we cannot observe these 6 extra dimensions because they are really small, so they cannot go really far. So the argument for this to be really small is this Calabi-Yau or this ambient space, this vibration should be compact manifold. Okay. So now let's do again the Feynman path integral for string theory. And as I explained before, from going to one point to another, then it will trace a surface. This surface happens to be a Riemannian surface. So it's a 2-dimensional surface that can be parameterized by the genus. You know, if you have 0 genus, then you have like a sphere, S2 sphere. If you have 1 genus, you will have the torus. There is a donut. If you have 2 genus, then and so on, right? So all these possibilities are allowed by the path integral formulation, and is given by, again, by this integral over a weighted. But now our moduli space is a family of Riemann surfaces. Yeah, and then we will explain this in more detail later on. We are talking about moduli space because this will then make the moduli space of Riemann surfaces, but we have to put some restrictions because otherwise, if you don't put some special restrictions, then this moduli space will be infinite, and then our integral will not be well defined. So we'll have some problems when you do the integral. Okay, so these Riemann surfaces that we explained before, they live on our Calabi-Yau manifold. So we want to do some embedding. so it lives in the fibers of the ambient Calabi-Yau manifold. So we do the embedding, we take this Riemann surface that we will call C, and then we will embed it in our Calabi-Yau threefold with complex dimension 1, so it has a real dimension 2. Okay, so now that we have like a configuration when you have different kind of surface, which explain how the strings propagate, then you can count these surfaces. And this is the great idea of Gromov-Witten theory, that will find a way to count these surfaces up to infinitesimal deformations. And we will explain better later on. This is just the introduction to explain maybe the ideas behind it. So Gromov-Witten theory studies the moduli space that we would call this curve M, counting algebraic curves in ambient algebraic varieties of complex dimension 1, 2, 3, and so on. Of course, this complex dimension should be, the dimension should be lower than the dimension of the ambient space. Okay, and now the moduli space is algebraic curve C in ambient varieties X is this family, and string theory gives us a family of these Riemann surfaces by our path integral formulation. So we will use insights from quantum theory, in the case of the string theory, of course, to obtain this counting of Riemann surfaces. Similar as the case when we are counting here how many possible paths are from one point to another for a point. Now we are going to count how many possible Riemann surfaces the string propagates. When I say strings propagate, is the string goes from one point to another. Of course, you can have other observables. You can also, actually, these calculations is related with the energy, what we call the free energy, and you have a sum over many genes of these Riemann surfaces. Okay, so as I say, this is a sum of many genus. For example, genus 1 will be a sphere. And later on, I will explain these red dots. Then you will have a surface with genus 1 in genus 2. And same as quantum field theory, we know that when you increase the genus, it means it's a is a less a more energetic problem, or a more energetic no problem, but a more energetic configuration. So it's less likely to happen, right? So because I say the path integral, you have this weighted probability of happening. So the less energetic, for example, genus 0 is more likely to happen. So it will be it will be it will associate a higher number than the others, right? Each of them is smaller and smaller, and this is the idea of perturbation theory. Okay, so these Riemann surfaces can deform, and because well, I haven't mentioned before, but when we do this path integral formulation, you know, in quantum field theory as well, in 4 dimensions, this is not a well-defined integral, because the family of path goes to infinity, so you cannot really integrate. So as you know, the only way to really formalize this path integral is by study a topological quantum field theory, right? Because in topological string theory, then you can do this integral of path up to finite automorphisms, which makes this moduli space finite. So as well in string theory, we will consider a topological string theory, because then you will have finite Riemann surface specified by the topological characteristic. So, but these surfaces can be deformed, right? And it doesn't really matter because you will just care about the topology, not the geometry. So it can be squished or can be pulled. We really won't care at the time of doing the path integral formulation, but there are cases where this you can extend it, you can infinitesimal deform to infinity, right? And then you will have some Riemann surfaces with this going to infinity. And then we will call this singularity. So in order to avoid the singularities, you will do a surgery, which means you cut. And then you study the cycles here. And then you identify this singularity with a marked point. So when you say this Riemann surfaces has marked points, it means you are associate a singularity. Of course, you have to put an extra term in the path integral, but this will be very, you can approximate this to 0, right? So at the end, this extra term is not gonna care, but we will then count these marked points or these singularity points on the Riemann surface, and it can have as many as we want. We can define n marked points. So we need a topological string theory, right, to have a finite model space, which means it's a finite Riemann surfaces up to orthomorphisms. And we want to introduce these singular points because they also will put constraints in how many Riemann surfaces we can count. So for example, in the case of genus 0 that you see here, then if you have less than 3 marked points, you can show the moduli space is not stable, which means the moduli space is infinite, and then the integral is not well defined. For the case of genus 1, you can show that you need to have at least 2 or more marked points in order to have a finite moduli space. So the moduli space is just the family that counts how many of these Riemann surfaces you can have up to equivalence relation. In our case, the equivalence relation will be these automorphisms. Okay, so I hope this is clear. Then I can show a picture of the classification of Riemann surfaces. Well, this is really with boundary, but you can just say this boundary will go to infinity, as I say here, like this. And then you can associate actually with this boundary a marking point, right? So this is a 0 genus with 0 marking points. This is 1 genus with 0 marking point, 2 genus with 0 marking points, and so on. Then you will put a marking point. So this is the same to have just the sphere with just 1 marking point. We will not consider as a boundary, but just a marking point. Then you have 1 genus, 1 marking point, 2 genus, 1 marking point, and so on. Then 2 marking points with 1 genus, with 0 genus, 2 marking points with 2 genus, and so on. So this is how the Riemann surface is classified. And each of these will give you a sum of an integral. Yeah. Each of these will have a moduli space. So when you do the integral of the whole system, you will separate on each of these will give you an integral. And each of these then will be defined a Gromov-Witten invariant, because each of these will give you information about counting or Riemann surfaces. Of course, this is the motivation for a string theory, but Gromov-Witten theory wants to generalize this concept to more general cases of surfaces embedded into, for the physics motivation, we have Calavillao as as our ambient space, but we can generalize to other ambient space. That doesn't need to be colored yet. Okay, so we can classify C not only by its genus, G, we can also use the homology class of the submanifold, which means we have C as our curve or rational curve, and then we have an embedding to our ambient space, and then we say the fundamental class of C in a way the push forward of the fundamental class will give you beta, and beta will be an element of the homology class H2 for our ambient space over the rational numbers. Okay. So this is how what this is doing is just giving an embedding of C, because you want to it's not whatever Riemann surface that you have, right? You also need to make the embedding, because this has to be inside our Calabi-Yau manifold. So we need to consider this embedding, and this topological information will be given by this push forward of the homology class of H2. Now, even if we fix the genus G, or if we fix the fundamental class beta, is beta, some Riemann surface could have infinitely many automorphisms, which is what I just mentioned. So, of course, you want to avoid overcounting, right? So we will count up to finite automorphisms. So this is when you really define the moduli space, because when you have a set of something, moduli, equivalence relation, you are just defining the concept of moduli space. So our equivalence relation in this case will be finite automorphisms. So when you count up to finite automorphisms, then you are not overcounting, because you are considering just one type of these Riemann surfaces. So in order to make sure our curve C given by the genus and by the homology class has finite many automorphisms, we need to introduce marking points, because as I mentioned before, these marking points will put some restriction on how many of these surfaces you have. But actually, as I mentioned before, the only really case that it's important to keep counting is when you have a genus 0 or genus 1. Otherwise, even if you don't have a marking points, but you have a surface of genus 2, then this will have a finite moduli space. So then it's in order to have everything well defined for every case. Otherwise, you cannot really define the path integral, because the path integral is counting all from genus 0 to genus n, and then you need to put this restriction to make all the path integral to make sense. Yes. So what is Gromov-Witten doing? So roughly speaking, is counting algebraic curves with fixed topological type, fixed homology class beta, fixed genus, up to finite automorphisms. So the number of all these curves divided by order of automorphisms. So of course you can have a number like 1/2, but of course you are counting algebraic curves, so it should be an integer, right? But because we are counting over up to automorphisms, this number that we will obtain doesn't have to be actually an integer, and then we have to interpret this number. Okay, so this is the motivation, and I hope let's maybe have some questions, if you have some questions by now. Okay, so I see a question in the chat. It says, Why do you need topological string theory? What about if it's not topological string theory? Okay, so you need a topological string theory in order to make sense, because if you don't have a topological string theory, you cannot really, then you have to count each of these infinitesimal deformations as a separate integral, because when you do a topological string theory, you really don't care about the geometry. So the metric can change, which means you can have a squish or pull manifold and it still will be the same. So we counted up to topological type. But if you don't have this, then you will count for all these different surfaces with different metric, and then this is not well defined, because then the moduli space will be no stable, so it will be infinite, and then the integral is not well defined. So you want this to be actually a topological theory. Does this answer your question? Okay, no problem. So, okay, so path integral formulation, since, well, usually people talking about Gromov-Witten theory doesn't really talk about physics too much. It says, oh, the correlation functions of the string theory is related with the Gromov-Witten, and yeah, but since there are a lot of math students, I want to maybe give you an introduction of what this really means and why this appears. So we are gonna describe path integral for this. So in quantum mechanics, we are going to have an experiment sending a particle from one point to our detector. Yes, and then we will put some holes here, and then see from which of these holes the particles travel, and then hits the detector. So this is, or we are going to do a mental experiment, a thought experiment. So we will denote the amplitude of a particle to propagate from the source X through a hole AI, and then to a point. And the point will be the detector, and then the amplitude will be given, okay, you create a particle if you want, and then you send it passing through a hole, just one of them, and then it hits the target, hits the detector. So this is schematically how we are gonna say. Then the amplitude, we say the whole amplitude of the experiment, because you really don't know in quantum mechanics which one of these holes the particles go through. Then the whole amplitude will be the sum of each of the single amplitudes. Okay, so it will be the sum. So Feynman has the brilliant idea of saying, okay, this will be the same experiment, but when you don't have any of the holes, it's empty. Yes, it's just empty space. You don't have any of the holes. But how can you, I mean, you have to really match with the case when you have two holes or one hole, because this is a very important experiment in physics where you have this wave behavior of quantum mechanics. So he showed, this was really, is a very basic concept, but nobody thought about this before. It was really brilliant. And he showed that even if we were in an empty space between the source and the detector, then the amplitude of the particle propagating is the sum of the amplitude for the particle going through every single hole. And then if you want empty, you have to consider that you have an infinite number of holes. If you have an infinite number of holes, then you have empty space between S and the detector. So his idea is, if we want to recover this, then we must sum the amplitudes for a particle to propagate from the source to the detector, following every single path. And this is the important part of the path integral formalism, because it has the information of every single path, and we are interested in counting this path. This is where we are really want. It's just that in the case of strings, it's not gonna be like a line, but it will be our Riemann surfaces, right? So we are gonna count it. When you count every single path, we are counting every single Riemann surface. This is the idea from physics to math. Okay, So then you say the amplitude of a particle from x to 0 at the time t is the sum of the individual particles from s to t in a time. We are going to set the time because we want to explain this from quantum mechanics, and then we have from quantum mechanics one operator to propagate a particle from one position to another. We will see this later. So for this, we take a path and approximate it by segments of straight lines, right? What it means is you are gonna take one single path and then you approximate this very small until you get to the detector. Okay, and then we left this every single segment to go to 0, so we make it really small to make it actually to translate this problem to a differential problem, really small. Then to build the amplitude for each path, we use the unitarity property of quantum mechanics, which this is how can you transform a state from one state to another. In this case, we want one state in a point to another point. That means if we know the amplitude for each infinitesimal segment, we can multiply them together to obtain the amplitude for the entire path. So this is what we want. We want to create just one little segment and then extend to the whole path. For now, we are just considering one path. So how can we do this? Okay, so in quantum mechanics, the amplitude of a particle to propagate from point qi, I for initial, to another point qf for final, in a time t, is given by the unitarity operator. So this is a state in quantum mechanics. I'm using the Dirac notation, but this is a state that lives in our Hilbert space. I hope everyone is familiar with this, but if you are not really familiar with this, then just believe me. And then maybe you can read some quantum mechanics notes and then come back to this. Okay, so we applied this Hamiltonian that I'm not specifying yet what it's gonna do. But now let us divide the time because we want really small segments. So I will choose the segments to be n number. And then this n, at the end, I will take the limit when n goes to infinity. Each of them with a duration of delta t, which is t divided by n times. We can then write, we will just separate this operator into small operators, which is translating, for example, the particle to this point, then the particle to this point, then the particle to this point, to this point, to this point, really small steps until it reach the detector. So of course, if you take the limit, you end up describing the whole line smoothly. So the states are normalized. This is a property in quantum mechanics. When you have these states, this goes to 0 if the states are different. If they goes to 1, if the states are the same. So we know that this Q form a complete set of states. Remember, these states lives in our Hilbert space, and we have also this property. Yes, the completion property. And then we put this between each of these. We will put this between each of these. Why? Because we want to compare this state with this state. This state with this state. This state with this state. Yeah, but n times. Yeah, and then we will say the n goes to infinity, so you have infinitive little points describing all our path. Okay, so you put this inside each of them, right? Have each of these n number of times you have. And of course, you have this integral because each of these will give you one of these. So you have this multiplied by n times. So you have n times integral. Let us focus in one of these. So let us take one of these, and then we will focus on this. And then we will assume, because we want to describe the easiest case, and then the easiest case is just a free particle, no interactions, just a particle moving from one point to another, no interacting, yeah, without potential, without any field that can change the movement, just a free particle. Just to describe the easiest case, because we are more interested in what is happening, right? So, okay, so we will take one of these and then we will replace the Hamiltonian. Of course, then you have, you can insert using this property of the momentum who follows the completion, because this is also another state. Then you can put it inside here. And then you know from quantum mechanics that this and this with this, basically this with this will give you some exponential of this. Yeah, when you are projecting momentum state over a position state, you get this from quantum mechanics. If you are not familiar with this, just believe me for now, that you obtain this exponential. Okay, but you can solve this. It's just an integral, right? For each of these single components. So for example, this I'm just taking one path, for example, from here to here. What happened from here to here? Yeah, that's what I'm doing right now. And then this is a Gauss integral. So you will have this, and then you can solve it by the Gauss integral, obtaining this. Then you can replace every of these single elements inside our total amplitude. And then if we replace in the total amplitude, then you will have, of course, this term to the power of n, because it's n times then this integral over a sum, because each of these will sum in the exponential. Remember that the q initial is q0. This is just a relabel. And then qn goes to qf. And now we can go to the continuous limit. The continuous limit, because we say delta t is t over n. If n goes to infinity, then t delta t, and delta t goes to 0. So in the continuous limit, because we want to make this really really small segments, then you have the delta t goes to 0, and then this they have here inside the exponential is just a definition of a derivative. So this q dot is the derivative of q in time. And then the summation over delta t is just the integral in the continuous limit of delta t. Yes, so we are going from something that is not continuous to continuous. Yeah, because we are doing yeah, it's exactly how you do calculus. So then we can define the path integral. So you are going to define over what do you want to integrate, and then you will take just this as our integration. And then you say that the whole amplitude will be given by this integration that we just defined, integrating over the exponential of here is 1/2 m of q dot from this change to the continuum limit. Therefore, to obtain this amplitude, we need to integrate all over possible path. So this is counting, this that we have is actually taking into account all the possible paths. Because you can, this integral, you can do a Taylor expansion, right? And then each of these terms in the Taylor expansion will give you one different path. Of course, the Taylor expansions is go even smaller, smaller, and smaller, and then these smaller components are the less likely to happen. So we will have contributions for the more likely to the less likely. So this is the idea. And then we need to integrate. Yeah, we need to integrate over the initial position and the final position. So in general, I can just describe this with our Lagrangian in order to have the or propagation of a particle from one point to another is just simply simply the integration weighted by this exponential, and this is counting all the path. So we show just from quantum mechanics path integral formulation. Of course, this approach is for one particle, but then you can take it and then instead of describing every particle in a point, then just you just you just have a field. In all the field is a function. Each point of this field, you can describe the particle. So how can we do this? So remember, in classical mechanics, this is the action, the integral over time of our Lagrangian is the action. Now, we can generalize the case with n particle system, n number of particles. So now let's take a general Hamiltonian, and then it's just the kinetic term of n particles. The mass of each particle is labeled by A, and then a potential. Yeah, it's a general potential which will tell us how each particle interact with each other. Now, or path integral formalism, we already know is just this integral with this weighted that depends on the action. And then, of course, the action, now you have the Lagrangian associated to this Hamiltonian, which is given by this. Anyway, now let us suppose we are only interested in phenomena at bigger scales. Yes, bigger scales, because now we are going to move from quantum mechanics to the quantum field theory case. So at bigger scale, the separation, we will suppose that this scale is larger than the particles, the n particle separation of each of them. Therefore, the level A can be replaced by the position vector. Yes, each of these positions, we will just give it by a vector. Then we can write that this QA, each particle, just depend on it's just one that depends on the time and the position. So usually we rename it and then we call it phi or field. In this case, we use phi because we use this phi to describe bosons, psi to describe fermions. So then this field is a functional called a field because it has the properties of a field. So the kinetic term, then we can change, yes, from this no continued limit to the continued limit by just exchanging, right, as our notation. So then we will recall the mass as mu, and then mu, we will call it like MA over L squared. But then we will assume that all the m's, because we are trying to describe like just one field, that it will represent just the same particle over all the space, and then it will have the same mass, and then you can, the integral, you just exchange it over 1L, and then the action for a single particle or for so many particles, you can just change it for the action of a field. This is just the same as what we do in classical field theory. Yeah, to describe. Then, or path integral from formalism, you can just describe it as a field. It's not it's a small field over all or space, and it's weighted by this exponential of the action. Okay, so now we are interested in physical observations because we want to do measurements, and then these measurements are given by what we call physical observables. Yeah, and these physical observables are given by correlation functions. So for example, you can do a correlation functions of charge where you want to measure the charge, or the correlation function of energy. And then this correlation is how you are interacting the fields, X and fields, and then it's just expressed by this. This will be important because these correlation functions are going to be actually interpreted as our Gromov-Witten theory, as our Gromov-Witten invariants. Yeah, then we will explain later on how can you do this. But now we will define the path formalism for whatever Lagrangian that we can define. And then we will choose this Lagrangian to be a topological string theory. So what is a topological string theory? It's just a topological quantum field theory. I explained already why we want this theory to be topological. So you take topological quantum field theory and you couple to gravity. So you include gravity. So the most use of this topological quantum field theory are two-dimensional gauge linear sigma models and two-dimensional Landau-Ginzburg models, right? And then Witten tell us how to describe this topological string theory and how to couple this topological string theory with general relativity, which is called gravitational descendants. And this is a way to generalize Gromov-Witten theory. So initially, Gromov-Witten theory was defined for topological quantum field theory, but then Witten tell us that we can include or couple to gravity by changing the correlation functions, and then this becomes gravitational descendants. So if you are more curious about this, I don't think I won't have time to cover gravitational descendants, but in all of the reference that I give you, it is covered. Okay, so now let's suppose we have our path integral formalism, and then we want to choose our Lagrangian to be the Lagrangian of a topological string theory, and then we will have the Taylor expansion will give you the perturbation theory, and all these terms will give you our Riemann surfaces, yeah, and they will be classified by their genus. And then, as I said before, then we will do the integration over the moduli space. The moduli space, as I say, is the space of Riemann surfaces, avoiding double counting. So you just take mod, you module up to finite automorphisms. So let me explain actually what is this. So I put F because actually when you do the calculation of this, you do the calculation for the free energy, what is called the free energy. You are actually describing the energy of a system, in this case of a string. And then when you do the Taylor expansion of course, I'm being talking very roughly, right? Because I want you to get the idea more than every single detail. We are going to focus on the idea because there are physicists and mathematicians in the audience, so I want all of them to understand at the same level. So when you do the Taylor expansion, you will have these these Riemann surfaces over the genus, and then each of these will have an integral. Yeah, plus another, plus another, plus another. And all of this, of course, when you go to more genus, in genus, you will have is less likely to happen. So it will be smaller, this value, than this value, than this value, in order to be finite. If it's not finite, then you can really measure anything. But anyway, let's say that the first one is just a genus 0 without any marking points, just without any genus 0. So it's a sphere. Then the next term will be genus 0 with one marking point. It's a singularity. Remember, it's a singularity that goes to the infinity, but then we cut it, we do a surgery, and then the extra term from this surgery will go here, but it's too small, so we don't care for now. And also remember, it's in topology, so we don't care about the particular metric or the particular deformation as long as the topological characteristic stay fixed. Okay, so the next term is just because I already explained, I can really show you in 2 hours talk, but you can see that if you have this with 0 marking points, then this will be infinite. So this won't contribute. Then you will have this with 1 marking point, only 1. And this also is not going to contribute because the model space is not stable, so it's infinite. Then you will have with 2 marking points is also doesn't contribute. So in fact, the only one who contribute at genus 0, well, not the only one, but the first one who contribute is just the genus 0 with 3 marking points. And then you can have the genus 0 with 4 marking points and so on. So this is a sum. As you can see, it's an infinite sum because you can have n marking points. Then you go to the next case, which is a genus 1 with 0 marking points. And this doesn't contribute because this model space is not stable. So the first one to contribute a genus 1 is with 2 marking points. So the marking points will help us to, especially for the, for genus 0 and genus 1, is essential to have the marking points because it will make us able to define these genus 0 and 1. For genus 2, you don't need to have marking points, but of course you also have the contribution with the marking point. So all of these, each of these is one of our, we will associate each of these given by the correlation function to our Gromov-Witten invariance. So this is the idea from string theory. Counting each of these count. So each of these are counting paths up to infinitesimal deformation, such that in each of these integral, the topological characteristic of the path are kept fixed. So this is the idea. So yeah, with this, our discussion about path formalism is over. Do you have any question? Okay, I don't see questions, so maybe we will then discuss Y-Calabi-Yau. So as I mentioned before, okay, you have a string theory. The first string theory is a string theory describing bosons, but the theory of bosonic string is not well defined. It has some states with a negative mass that you cannot really get rid of them. So you have tachyons. That's why it's called a tachyon. So this tachyon has the property that propagates with greater than the velocity of light, and we know this is not possible. It's not physical possible. It has negative mass, so it doesn't really make sense. So in order to solve this problem, and because the universe is not only made of bosons, we also have fermions. So in order to include a theory of strings with bosons and fermions, then you need to include supersymmetry. The supersymmetry is a symmetry that relates a boson with a fermion, or transform a boson into a fermion, or a fermion into a boson. So for mathematicians, then this is just you are extending the Poincare algebra to a supersymmetric or super Poincare algebra. So it's an extension of an algebra. Of course, in nature, we haven't observed yet supersymmetry. Some people have supersymmetric models for the standard model, but they haven't been seen at CERN in LHC yet. So some people don't believe in supersymmetry, some other people believe in supersymmetry, but it's the only consistent way to describe a string theory. Okay, so if you have a supersymmetric string theory with bosons and fermions, then this theory predicts that the universe has a 10-dimensional space-time. So it's a 1 time coordinate and 9 space coordinates. but we only observe 4, as I said before. So you just do a vibration, which means at every point of our 4 space-time, you associate a manifold, and you want this manifold to be small, so it's a compact manifold, and we will describe why then has to be a Calabi-Yau manifold and no any other manifold. So there's not a consistent way to break symmetry from a string theory. If you break, of course you can break symmetry, but then you generate tachyons. So your theory is not unitary anymore, and then you have some physical problems that you don't want this to happen. So you want to keep the supersymmetry at all points. And then, of course, when you do the compactification, you just are describing effective theory. An effective theory, which is then the effective theory, you also want it to be supersymmetric, right? Because for this problem of unitarity. So in order to be supersymmetric, then this creates a physical constraint, a physical motivation, and is the space or ambient space X must admit a covariantly constant spinor. Yeah. So a covariantly constant spinor is when you apply the covariant derivative to the spinor goes to 0, because it's invariant. But then if you have taken a Riemannian geometry course, or if you have taken general relativity, you know that these covariant derivatives define, or we can define through covariant derivatives or Riemann tensor and or Ricci tensor. But if you apply this definition of the Riemannian tensor to our spinor, then we obtain that this Ricci tensor has to be 0. So the fact that you want our effective theory to be supersymmetric, then we obtain the restriction that this Ricci tensor should be 0. This is equivalent to say we want the metric with holonomic group SU3. SU3 because you are describing this compact manifold as a complex dimension 3. So it's SU3. Okay, but this is from the point mass of view, what is equivalent. So from complex geometry, you have the first Chern class. Yes, the class of a complex vector bundle. The first class is related to the cohomology degree 2 of our ambient space X. And this is given by the Ricci scalar. But if our Ricci tensor is 0, then of course the first Chern class is gonna be 0. It's very easy to see it. So of course, then from supersymmetry, we will have all this. The manifold should be compact. The manifold should be have a Ricci tensor 0. The manifold should have a holonomic group SU3. And then the Chern first class should be 0. All these statements are equivalent actually. Okay, so theory which have all these properties is just basically a Calabi-Yau. So this is our motivation of why we want a Calabi-Yau manifold. Okay, so a Calabi-Yau manifold is a complex manifold that is scalar. By the way, this Friday there is a talk by Daniel Hubrick about how to do algebraic geometry in scalar varieties. So we will discuss this. Maybe I thought maybe I give a little introduction, just explain what is scalar variety. So a Calabi-Yau manifold is a complex manifold, scalar, and admits a metric which the metric associate with the Ricci tensor associated with this metric vanishes. Yeah, this. Okay, but then we understand what is complex, we understand why admits this, but then what is a Keller? Okay, so to be a Keller, let M, J, a complex manifold, where J is an almost complex structure with an Hermitian metric. This Hermitian metric is just how this almost complex structure is related with J, has some kind of nice properties, and then a Hermitian form omega, such that G is a calorimetry if this Hermitian form is closed. So this is the definition of a closed form. I hope everyone is familiar with forms, differential forms. Okay, then we call this form a Kähler form if it has these properties, and a Kähler manifold if our manifold is complex and it has an almost complex structure and has a Kähler metric. So this is roughly speaking, this Kähler manifold. It's not very clear, but I cannot go more into details. Just please go to the Daniel Huber talk. Okay, so let's see some simple cases, the simplest examples of Calabi-Yau manifolds. So we will consider some complex subspaces of projected and complex projected space. Okay, so when I write these subspaces, these are contained in our Pn, and then we will describe it with a polynomial of degree d. So we will describe this as an algebraic affine variety, where you describe the variety with a polynomial, and then you see all the analysis that we learned in the course in algebraic geometry. Okay, so this is the complex dimension. So if this is complex dimension 1, then you will have a real dimension 2. And then the Calabi-Yau here is a polynomial of degree 3 inside. So this is a polynomial of degree 3, for example, something like this, plus something else. And this is inside or P2. Okay, of course, you can have more polynomials of other degrees here. For example, you can have polynomials of degree 2 or 5 on P2, but this won't have the condition that C1 is equal to 0. And because it doesn't have this condition, then those examples are no Calabi-Yaus. So these are Calabi-Yau. You can show that this one is a polynomial of degree 3, you have a Calabi-Yau, and this is a torus. Similar for the case of n equals 2, for complex dimension 2, then you will have a polynomial of degree 4 for P3. Remember this, for example, this P3, these are inside or P capital M. So this will describe something that is called K3 surfaces. But the most important case is when is complex dimension 3, because this is the number of dimensions that we want in physics, right? From the compactification of 6 dimensions, we want 3 complex dimensions. So this is the important case. The most famous case of Calabi-Yau is the polynomial of degree 5 in P4, and this is the quintic. There is a really nice talk by Xenia de la Osa, and which she, with Philip Candela, Green, and Parks, she used the quintic to define the number of rational curves in the quintic Calabi-Yau triple. It's a really nice talk. She introduced this from the physics point of view, and she did the calculations to obtain the number of these rational curves. You can go and check, but from the physics point of view, which was groundbreaking by the time, because mathematicians couldn't calculate this number of rational curves, but physicists could from string theory. So it's really nice, and this is the structure of our quintic Calabi-Yau manifold. Okay, so we can have n until n, and then you have Pn with a polynomial of degree n plus 1, and all these cases has they are Calabi-Yau, so you can show that this all has first Chern class equals to 0 and has a Kähler structure from inherit the Kähler structure from P and capital N, all of them. So of course, these are the simplest cases. You also have more advanced cases. For example, you can have Tori varieties. You can have a Pn's products. You can have product of P2 times P3, for example, and then you can see this described by Calabi-Yau, depending of the degree of each of these. You can also build Calabi-Yaus from quotient manifolds, etc. So how can I, this is the logo of Physics Latam, and this is a Calabi-Yau, of course. It's a threefold Calabi-Yau, or at least, of course, we cannot show a two-dimensional trough of something that is three complex dimension, but this is kind of the representation. And then this is how the space-time looks like. This is the vibration. So at each point you put a Calabi-Yau. And then, of course, this Calabi-Yau can deform, can move, and this deformation will be taken into account when we define our Gromov-Witten. And this is why we are defining this, embedding this function f that give us the push forward of curves, and we define it to be or fundamental class beta. Okay, so this is how space-time looks like, where every point is a Calabi-Yau. Okay. So is there any question to here, up to here? Yeah, you can also write in Spanish. It's fine. Maybe I can just answer in English, but the question is in Spanish. There's no problem. Okay, so somebody is asking, is this constraint, is this supersymmetry comes from math motivation or physics motivation? And the answer is, it comes from physics motivation. You want this effective theory to be supersymmetric, because there's no way to keep the theory unitarity. And then in order to keep it supersymmetric, then the fermions should have some properties, and then this property is basically to be covariantly constant. And then, of course, from physics motivation, but then it leads to mathematics implications of or ambient variety. I don't know if that answered your question. Thank you. Okay, no problem. Is there any other question? Okay, if there's no more questions, then I will continue to explain moduli spaces. Okay, in algebraic geometry, a moduli space arises as a classification problem. Generally speaking, a moduli space M is a space or a family of objects that belongs to a total space A under equivalence relation. In our case, in the string theory case, we have this total space as the space of Riemann surfaces up to topological characteristic fix. You also consider, remember, you consider the genus, you consider the market points, and then you mod up to equivalence relation. And this equivalence relation in our case will be the finite automorphisms. So usually a moduli space is a natural equipped with a topology and or not necessarily has and or geometry, reflecting the properties of the object in A under the equivalence relation. That means it codifies the information. So You have information like how close two classes are from each other and how they change, how they degenerate, and the existence of a special object with singularities, for example. Then moduli. So we will start with the easiest case. We are just gonna take into account just one parameter, and is the genus. So you have two moduli space. This is non-compact, and then if you put the bar on top of this curve M is the compact case. So in this case, you have moduli space of genus G. And in this case, since you don't have marking point, you have to impose the constraint that G has to be greater or equal than 2. And then this will give you non-singular curves. If you have lower than 2, which is genus 0 or 1, then your moduli space is not stable, which means that it is infinite, and then you don't have the integration. So same case for the compact case, you also have to impose the G is greater or equal than 2. This was studied by the line Moonford, and then this is called the line for stable curves moduli space. And then C is a nodal and connected, or C, you remember that we, in complex, since it's a complex dimension 1, we just describe it as a line. And we have a line. So let us consider nodal. So nodal will be these points. Well, you have these, well, I will show you will have these singularities, and you have this cross. So this is a nodal, and the nodal also will count the same. It will be denoted as a special point. So you will have two different types of special points. One is the nodal, and one is the market point. These singularities that you just go to infinity, but then you just cut. Okay, so how can you describe this in R2, in complex dimension 2? Then this is just this picture when you have the nodals here. Yes, and you have this one and one genus, and then yeah, this is how it looks. But in complex geometry, we are just counting it as a line, as a chord, of course. So this is the idea. For us, a nodal will be a complex algebraic variety of dimension 1 with a worse nodal singularity. This is a nodal course, and then this is the nodal singularity, where you have equations like this. So it's not very clear if x or y is the one to be 0 or both equals to 0. Okay, so this is the idea of the nodal. Now, usually a nodal curve C will be assumed to be, this is something that we will require because we want things to behave properly. There's no like weird singularities, so we want this to be connected. Well, you can see it from our case of Riemann surfaces, they are connected. We want them to be complete, which is the same as saying that they are projective, and not irreducible. We also want that they not to be irreducible. Okay, then this is the case for when you have just taking the information of the genus. Now we are going to take the information of the genus and the market points. So this is the moduli space of genus G and pointed. So this is a non-singular curve. And then you will have the line Moonford case, which is the stable curves. This is compact, and then they show that this is only possible if they have this restriction of 2g minus 2 plus n is greater than 0. And this is just gonna give you the case where g has to be, if g is 0, then n has to be equal to 2, greater than 2, so it means equal to 3. And if g is equal than 1, then n has to be greater than 0. Okay, so C is a nodal and connected. Same properties as we mentioned here, and then you have the P represent the positions of these marking points from P1, Pn. Then these are distinct points. Each of them has to be different, and each of them has to be different than the nodal point. So it cannot be here, it has to be just in any position where is the singularity, but not the same position as the node. Yeah, this is this goes to singular locus. So now, then this the line moon for show the dimension of this moduli space. So this is moduli space of stable curves is non-singular, irreducible. Actually, is the line moon for stacks, or has the structure of an orbifold. We will describe at the end of this section what is the meaning of stacks, and it has an interpretation as a functor, but we say we want to integrate over the moduli space. But what is integrate over a functor? What is a point in the functor? So we will see this, because we can, well, basically we can just associate an algebraic variety to these stacks, or to this moduli function. So they show that the dimension of this moduli space is 3G minus 3 plus n. Okay. So if following this constraint for the genus and the market points. Okay, so this is the moduli space of a stable curve, but we also have to remember that we also are counting our curves up to embeddings, onto these embeddings of our ambient space X. So now we need to describe the moduli space of the stable maps. So let S be a non-singular projective variety, then we will consider these maps. So F is an algebraic morphism that takes our curve C and embed it into X. Next is the ambient space of target. And then this is a complete connected nodal curve of genus G, just basically these requirements that we ask. And then remember that the push forward of C it lives in the homology class of degree 2 of our ambient space X over the rational numbers. Okay, and then this moduli space of stable max now has has 4 different information. Has the genus, has the market points, of the ambient variety, and it have the fundamental class given by this. So it keeps the topological information of our ambient space X. In the case of string theory, we want this ambient space to be Calabi-Yau. So is the moduli space of stable maps. The previous one was stable curves, because we are just counting curves. Now we are counting curves embedded into ambient space X, and then this is stable maps, because this gives you the map of genus G to X, representing this fundamental class. This is just what I just explained. Now it has some properties. For example, this class, let's suppose this class that lives inside is a moduli space, is stable if and only if the number of automorphisms is not infinite. So it's stable. Say it's stable is the same as it's finite. So an automorphisms of F is an automorphisms of C, and then we have this universal property, which is just a diagram that commutes. It means you have a morphism from C to C, and then the F should go from C to X, and then another map C to F in order to this diagram to commute. And then we say this, if you have an automorphism of this, then this should be also an automorphism. Okay, but then automorphisms of F are constrained by automorphisms of C, because taking into account how many automorphisms of this curve C exist. So there is a, I mean, it's very easy to see if automorphisms of C are finite. This implies the automorphisms of F are also finite. And then we say F is stable. So this is easy because then we need to focus is just in automorphisms of C and then find a map, a morphism F that is it commutes with this diagram, and then it tells you if it's stable or not. Then we, of course, we will have this the line moon for stacks. They might be reducible or non-reduced and very singular. Yeah, in principle, this is stacks or the algebraic variety that we will associate with these stacks. They don't need to be smooth, but this is in general cases, right? It's not always the case. So let's give this definition. Left this moduli space of the compact moduli space to be a functor, which means takes a scheme from the category of schemes over these complex numbers to a category of sets, and then we will associate this is a element of the category of sets. So we are going to associate a fine variety to our functor. Remember, these stacks can be stacks are in the sense of category theory are covariant functors. So, but we want something to integrate over, right? So then you define this course. These are called course. Sorry, course. They are called course moduli space, and basically it's the family of these maps that takes C to or scheme S in order that each of these points take an element of S to C up to isomorphisms. And the same case for the compact case, it's just it will describe the unstable curves, these two families. And we keep it up to isomorphisms. So for example, let's give a theorem where I state these definitions, because here I'm just defining what are these elements of this set of scheme S. So, okay, the theorem say that when G and N are positive or zero, and then we keep the dimension of this, the line for moduli space, then there exists a coarse moduli space. That means for this core Bn, which are these or stacks, then we will associate these schemes to go to sets, and then the sets are going to be this coarse moduli space respectively. So if you have a non-compact, you will have this moduli space with a straight and compact, and then this is compact, you will have the compact case. And the theorem say that there are normal algebraic varieties of this dimension 3g minus 3 plus n, and we want this because we want to define the integral. So we want to be able to integrate. So so now we solve the problem of having something that is a functor to something that is an algebraic. And it has other properties, like, for example, the variety. This coarse moduli is irreducible, projective, and has quotient singularities. Then, well, I will put these notes on the internet, but maybe it's just extra information. We don't need to go so much into detail right now. But let's consider an example. For example, the smooth curves of genus G equals to 0. So parameterizing these smooth curves in interior or coarse moduli 0, with n marking points, then we have the constraint, right, of the how many of genus and n I can have in order this moduli to be stable. Look that I'm not describing right now. I'm not describing the moduli space of the stable maps. I'm describing the moduli space of stable curves. So I'm not taking care right now of the embedding to the ambient space. So of course, when genus is 0, then you have this constraint, and then n has to be greater or equal than 3, or at least 3. So we know that any smooth genus 0 curve C are isomorphic to P1. I hope the people from the algebraic geometry course remember this. And then this is basically the automorphisms of P1 are the projected general linear group over the complex, projected linear group. And then this projected linear group are just a family. A, C, D is a matrix of the projectorization of this M2 times 2 matrix. And this is basically just a P3. This lives into P3. And then following the determinant is different than 0. Such that how this projected general linear group acts on P1 is given as follow. So these are the coordinates in our projected P1. I hope you remember. Because we describe it. And then A multiply X plus BC. This is our new coordinate. And then this is the other coordinate. Now, the action of automorphisms of P1 is 3 transitive, which means it takes 3 points. Okay, let's suppose, for example, that you don't have these 3 marking points. So the fact that gives you infinite is because you have a infinite family of actions. You can basically, you have infinite of this, there's no constraint for this, and then you will have a moduli space that is infinite, is not stable because you have so many of these infinite. So when you put the 3 marking points, basically you have 3 points over P1, and exists a unique element is where this sending the 3 points to 0, 1, and infinite. So these 3 points send it to this P1, P2, P3 are sending for these 3 points in P1, and then you can put a constraint on this in order to don't be infinite up to morphisms, to automorphisms. So consider the case n equals 3, then every curve you will have C, and then the 3 points that lives on our moduli space. Well, here I'm saving the stacks, but over space C, and then this is our straight M or course M03. And then you will have our curves to be isomorphic to P1 with these 3 points, and every 3 points are always sending to 0, 1, and infinite. It doesn't matter where you put the points, the action of this PGL is sending always to the same variety. Then up to isomorphisms, there exists a unique smooth G1 curve with distinct 3 marked points. And this is just a point because all these different varieties are sending it is isomorphic to P1 with 0, 1, and infinite. And then the moduli space is just a point, which is the same as the spec of the components. So this moduli space is just a point. There's nothing else. Now we can describe maybe some more general cases. So for example, the stability of coarse moduli space with n marked points that is compact must have at least 3 special points, can have more, but at least 3 to be stable. So if n is lower than 2, then we say that this is empty. Yeah. We say that this is empty just to, in order to be well defined, we assign an empty space. Then for n equals to 3, this case, we already defined a point. There is a point. I hope you get the how we can maybe calculate this moduli space. I don't have time to do more difficult examples, but maybe I give you this. Then if you add one extra point, then you will have P1 removing this point, because these points are already fixed, and then you have just a P1 without these 3 points. And then for whatever n you want, then you will have a finite moduli space, which of course it gets a little bit more involved when you put points, but it's following this with more points to play. And you, of course, you have to count it up to isomorphisms. Then another case is a small course of genus 1, and then you have this is again empty when you have n is lower or equal than 1, and 1 is finite when n is greater than 1. Okay, so from n equals 2, you have something that is finite, is well defined. So a small course of genus greater than 1, then it doesn't, for g greater than 1, it doesn't matter the n. For every n, this moduli space is fine. So basically, this is how we are defining these moduli spaces. Of course, the moduli spaces of stable curves, when it comes the x and beta, is more involved, but this is just to give you an idea of how you can calculate the moduli spaces. You can go to any of the reference that I gave before. It's really nice. Okay. And is there any question on up to here? Okay, if there's no any question, let's go to the main part of this talk, which is Gromov-Witten theory. And then let's start by defining a Gromov-Witten class first, and then Gromov-Witten invariant, because we are going to get the invariants from Gromov-Witten classes. So let's suppose I have, from now on, I will just discuss about the coarse moduli space. Maybe I won't say any more coarse. But then, you know, this is the algebraic variety associated with the moduli functor, or the line Montfort stacks. So you have two maps. So one map, it goes to x and times the product of x. And the other map, it goes, is a forgetful map. So it's forgetting our map. So it's taking us from the moduli space of stable maps to the moduli space of stable curves by forgetting the information about the map. Okay, so the first map, P1, given a stable map where you have a core C with M marked points, you send them to X, we get a well-defined N tuple, which is evaluated this FP1 dot to dot FPN inside or X to the power of N. Look that this N is the same N as the marking point, okay? And it can be shown that T1 is a morphism. Now, for the map P2 that I say it forgets the information of X and beta, then you have F taking the curve C and the N market points is a stable map, then C no need to be stable, and P2 can be seen to be a morphism as well. Okay. And then, okay. Then let's assume let's assume that X is a smooth projected convex variety, then our moduli space of stable curves is an orbifold, and we want this orbifold structure because we will soon use or Poincare duality, a Poincare duality, which is a map between homology and cohomology. But then in order this to be well defined, we need this to have an orbifold structure. And then the line in Mumford, they calculate this, well, I think it was the line in Mumford, but they calculate this expected dimension of this modular space, which is given by this expression, where this omega x is the canonical class of our ambient space. In our string theory case, there will be the canonical case of our Calabi-Yau, but remember the Calabi-Yau C1 is equal to 0, so this case will be 0, and then you will have the other numbers to be determined. So now let's consider a map. Remember the P1 takes this to here, which is takes this moduli space of stable maps. It takes to x to the m. And now if we do the pullback, which is a pullback of this, is a map between cohomology classes. It takes the cohomology class of or stable map of a stable, sorry, the cohomology class of ambient space to the power n, to the cohomology class of or moduli space of stable maps over the rational numbers. Furthermore, you also have this map P2 that goes to the moduli space of stable maps to the moduli space of stable curves, and then this induce a map, which is the push forward. It goes from push forward to homology class of these stable maps to the homology class of stable curves. And if you want to compare these two, you want to do something like this or something like this. But then this lives in cohomology class, and this lives in homology class. So how can you really go from one to another? Then this is given by it will be be useful to use the Poincare duality, because the Poincare duality transform homology from cohomology. And then this is what is called the Gisin map, or Gisin morphism, which is given by this symbol, and then you will have P2. And then what is this actually doing? This is taking this cohomology class of a stable, basically this, of a stable curves, and then bringing them to M2 of this, to the cohomology of stable curves, where G is our dimension, the dimension that we determined here. Here should be with a N2. Let me fix it. Very close, and yeah, to be in agreement with this. Okay, and then if we take, remember that this P2 is just the push forward of this homology class to this homology class. Now let alpha be an element of this homology class of stable maps. And then if we apply our Gisin map, then what is this doing? This is taking this homology class and applying the Poincare dual. Once you have this Poincare dual, which is having then on this class, then you apply the push forward of P2 to have it in this
homology class of moduli space, and then you wanted to bring it back to the cohomology, so then you apply the point caret dual. So this is basically how can you compare this with this, because they live in homology and cohomology classes. So then you do this by the point caret dual. So now let us define the Witten class. So the Witten class will be an element of this homology class of stable curves. So it will live in the homology of this. And then we will just put them up. So you have this number of elements living on the homology of stable maps. And then you apply these, all these maps that I already defined. So what is this doing? So what is this Gromov-Witten class? So this is precisely give the homology class of a set of curves in X. It's giving topological information of these curves in when you embed it. So you have X, you have a map that takes the curve with n market points to our ambient variety, such that you keep the fundamental class fixed. Remember, this is H2 of X over the rational numbers on reference, consider over the integers, but I mean, in a more general case. And let's say that each of these, you are mapping the points to cycles. Yeah, each of these F takes one of the marking points and put it into a cycle. Yeah, and this cycle lives in X. Remember that the cycles are closed loops or the higher dimensions equivalents of these loops. And then the cycles lives in X, and then with the point caret dual. So these lambdas that you see here are these point caret dual of these cycles. And then this lambda lives in this cohomology class of X. And then let's do this is maybe quite abstract to grasp. Maybe it's quite difficult to understand in just a talk of 2 hours, but then let's try to make a draw of this and give an intuition, and then maybe you can study by yourself and try to understand what all these maps is doing. Maybe it's good to go step by step and then see, okay, this map goes to here, and what is the meaning of go from here to here, and then from here to here, and then playing with the point caret dual to see how you transform from homology to cohomology and so on. So, okay, so let's suppose we start with a curve C with n market points. Remember this, we will take it to live in the moduli space of stable curves. And then this map will embed it in X, where we will have cycles. The cycles here are the things that we want to count. And then in each of these, then the image of F, which will be this, it will be this curve, the purple curve. When it touches the cycle, we will put this as our F of Pi. Yeah, so the market point we will associate with the cycle, and this cycle will be then applied the point caret dual to live in this cohomology class of X. So we will do this to keep the topological information when we do all these embeddings. So this is counting, then this go here, and then the other market point is touching the cycle of C2. And then we will have to specify what are all of these cycles. If this is the same degree for all of them, if all the cycles are lines, or all the cycles are a surface or a hypersurface, or you have a combination. You have a line, a point, a surface, and then how intersect with each other. So basically, we are counting the intersection of these. This is roughly speaking what is happening. So for C1, if you have one cycle, for example, should put Ci just to
be more general. So the Poincare dual, I mean the alpha, lives in cohomology class of X over the rational points, and then this is what we denote as alpha I. So okay, we have this our map, and then what is this in our string theory picture? So we have the space-time dimension 4, then you have the 5 regions, which are Calabi-Yau, and then you will have these Riemann surfaces that you have here. And then where you have these market points, remember these are singularities that you just do surgery to, and then you associate a marking point. Then these marking points, you will associate these cycles are passing through the marking points. So this is basically this FBI. Okay, and then you are just trying to count how many of these you have. So this Gromov-Witten class lives into the cohomology of the stable curves. So now if you want to get an invariant out of this, then you need to get a number, and the way to get a number is just integrate. And what are you integrate out of the moduli space. So this is basically what we are gonna do. But before doing this, then we can maybe calculate the sort of dimension, but this is just a cohomology class, so really doesn't have an interpretation of dimension. So we say the degree of this Gromov-Witten class. And then this is given by this expression, which this is the line bundle in Calabi-Yau, this is 0. And then this counts the degree of this alphas associated with the cycles that we are defining. Now, Gromov-Witten invariant, as I say, we want a number out of our cohomology class. How do you get a number? Then, well, you will integrate. You will integrate because this lives in cohomology class. This class lives in cohomology class of moduli space of stable curves. Then you can integrate over. You can integrate over the moduli space of the stable curves. But remember, you have the restriction of the moduli space, the dimension of the moduli space by the line Mumford studies. And this integral is just basically taking the Gromov-Witten class and capping it with the fundamental class of this moduli space. So this is what Gromov-Witten is doing. Gromov-Witten invariant counts how many Riemannian surfaces can be inside or ambient variety X, such that the push forward of classes of Riemannian surfaces with the fundamental class fixed and with the marking on the original domain curve exactly get pinned to the end cycles psi X. So this is basically counting how many of these do you have where you keep this. You associate these marking points with the cycles. And okay, and then we want this Gromov-Witten invariant to be deformation invariant, because as I mentioned before, when I was talking about Calabi-Yaus, then you have this, the Calabi-Yaus can have deformations. This has on physics interpretation, but I'm running out of time. But basically this, the X is not fixed, it can be deformed, and then we want to study the deformation of complex and Kähler structure of our ambient space X. And in order to get deformation invariance, then we need to replace the fundamental class of our moduli space with a class called the virtual fundamental class. Yeah, this is to say the tangent bundle or the line bundle of the space, the dimension is not fixed. Then if it's not fixed, it's not smooth. And then if it's smooth, then the virtual class matches with the fundamental class. The virtual fundamental class matches with the fundamental class. But if it's not smooth, then you need the virtual class to make sense out of this deformation invariance. Right. then this virtual fundamental class live in the cohomology also of this moduli space of stable curves. Then again, the Gromov-Witten invariant will give us numbers of counting structures, curves embedded into our ambient space. It's just the Gromov-Witten class capping with now the virtual fundamental class. Of course, virtual fundamental class is a big subject. Is hard to explain in just in this time that I have, because I have to cover a lot of stuff, but you can see more information about how can you define these virtual moduli spaces in the reference that I already gave. So if, as I say, if our moduli space is smooth, the fundamental class is sufficient. Yeah, I mean, you don't need to go to define the virtual class, but this is not the case. The tangent shift of our moduli space is not locally free. There is an obstruction, basically what I was talking about, the dimension of this tangent bundle. To be a vector bundle, therefore, our moduli space is not smooth. Look, all this has been defined over the moduli space of stable curves, but you can also, let me see if I cover, I don't think I covered it, but you can also define, the integral over the, if you want to avoid the use of the Gaussian map, you can just take up to here for the Gromov-Witten invariance, and then you just define the integral of this, and just define the integral of this. Or now you integrate, I should have put it, you integrate over the moduli space, but of a stable mass. And then you don't need to do all this. The Gaussian was to explain the Gromov-Witten class, but the Gromov-Witten invariance, you don't need the, oops. Okay, give me a second because I closed my tablet. So to get the Gromov-Witten invariance, you don't need to go the Gaussian, you just need to do this pullback of P1, but then integrate. Here you are integrating over moduli space of a stable curves, but then you can just integrate over the moduli space of a stable maps, and it will make sense, and then you can define or Gromov-Witten, will define our Gromov-Witten invariance like this. And maybe it's more easier for you to see what is happening here, because then you don't need to take care about this Poincare dual and then changing from homology to cohomology and so on. Then using the push forward formula, which means from P2, well, from the moduli space of stable maps to go to the moduli space of stable curves. And then remember that you have this map. Okay, here explain it. Here is already explained that you can just actually jump all this and then just integrate over just the pullback of P1, but then you change the integration of the moduli space. And it's doing the same. It's also counting the same thing that we are counting here. Here. It's just that maybe it's a straightforward definition. And this makes sense. I mean, the Gromov-Witten invariance makes sense even if we don't fulfill the requirement of the dimension for stable. Although the Gromov-Witten class makes sense only, so you can define Gromov-Witten class only when the moduli space is stable, which is this constraint of n plus 2g equal greater than 3. The Gromov-Witten invariant, yeah, it makes sense for all genus and all n. this is very nice. You need to do all this of Gromov-Witten class, but I just want to be self-contained and maybe tell you Witten class from Witten invariant, so you have an idea when somebody mentioned this. So now we cap it before this integral is just capping. Before we cap it with moduli a space of stable curves, but now we are capping it this map with the virtual. Remember, you have to keep in mind that is the virtual fundamental class. This is left to show that if we consider then the virtual fundamental class of a stable maps, then this invariant is the formation invariant. I'm not gonna do this, but you can prove it. You can read the proof in the books. And then in the literature, there is actually this is a little bit of a mess because every book uses a different literature for these P1 and P2 maps. But then other literature that is very, very, very famous and used a lot is that it is convenient to rename this P1 in terms of its components. For each of these stable market points, and then we will define an evaluation maps. Yes, for each of these maps. For each of these stable. For each of these marking points, then you will have an evaluation map, which takes this modular space of stable curves to remember that this is not anymore because it's not the curve. This is we define this as an algebraic variety, so it makes sense. All these maps that I'm defining, and then by sending this stable map of the curve with n marking points to X, which each of these be fixed in the cycle, and then we have the definition, basically composing with the projection. Yeah, we have this definition, and then you can find the other way to define the Gromov-Witten invariant is with these evaluation maps. And then this is if you go to another book and maybe you don't see the definition that I'm telling you here about the integral, but then you see this definition of the intersection of each of these evaluation maps on these alphas, where alphas are the Poincare dual of these cycles, and the cycles are fixed in the position of the FPI. PI is the position of the marking points. Okay. So let's give some examples, and then I'm done. So the first example is just let's assume X is Pn, yeah, and then recall this is the fundamental class. Remember, beta belongs to this, and then this is the fundamental class of P2. Will give us a rational number. We can write that this fundamental class is just D times a line, yeah, a class of lines, such that all beta belongs to this homology class. Then we will have this modular space. Look, that now I'm doing modular space of a stable maps, considering this as X and then this as beta. Then we can show that the dimension of this modular space is D and D plus N plus D plus N. Capital N is the degree of our projected, dimension of our projected space, but this lowercase n is the number of marking points. And this related with our projected space. Then we can just count enumerative lines in a plane. Let's say, let's have 2 points, P1 and P2, and then a line living in our projected space 2, such that these 2 points belongs to a line. Yeah. If and only if can be parameterized by a map. Let's say this P1 is a map
from P1 to L of degree 1 such that the points P1 and P2 belonging to this PI, and then we will associate these marking points with the points inside our line. Then we will have the map of the course with these two marking points, and then we will go to P2. And this has the image of this will give us the line. As remember when I draw this X, and then you draw the image is the line that passes through all the cycles. So this line will be this L, and then the cycles will be fixed in P1 and P2, and these cycles are just dots. Now then, let alpha be related to the homology class of P2, then the hyperclass. Well, I mean, you have to define all this because you need to do the integral that I just mentioned, right? So you need all this information. You see, it's not so straightforward, but it's easy. It's not straightforward, but it's possible to do. So before Gromov-Witten invariant exists, it was really difficult to do this. Well, these cases are very easy to do, but then the problem gets really, really hard to do. For example, in the case the quintic, how many rational curves you have in the quintic is really hard to count. This is something that I already explained, but mathematicians by that time couldn't make it, but thanks to this kind of way to do it, and from the physics information, then we can obtain these rational curves. Okay, so this alpha belongs to this cohomology class, then the hyperclass is the hyperplane class. Class of points of P2 is alpha 2. Then we can calculate, because we have all this information, we have n, d, and the lower n, then we can obtain the dimension for this moduli space 0, 2. And then if we calculate the integration of this, it will give you 1. So what does it mean? It means that there's only one line passing through 2 points inside this P1 we have. Let's see other case. So for example, we have the Witten, Gromov-Witten invariance of this of 0 with n3d minus 1 market points. This will be the moduli space 0 for genus and 3d minus 1. Then our ambient space will be P2, and then with the beta. Then we will obtain a number that depends on beta, and this will be the number of rational curves of degree beta that passes through 3.d minus 1 general points, which are given like this, related to our cycles. And of course, you have this, the marking points will be the points that this intersect. So this is the intersection interpretation of this is why I call in the first place this called enumerative geometry. Study, this is something the intersection theory studies, to enumerate how many curves pass it through a point or through other kind of surfaces. So another example is a P3. Then you define this information, and then you define these 4 cycles, and then this will give you the number of incident lines to 4 given lines. And this will be related with the punctual of the cycles, and then the cycles are fixed in the position of these 4 lines. Then for P3, then look, now I'm using a different degree because now I'm using different cycles, so different degrees of cycle, different structures. So this basically will tell us the number of twisted cubits meeting 6 lines in 3 points. So you start to do more difficult and intersection theory of different structures, and then see what you obtain. It is possible thanks to this Witten invariance. And the number of this is 190.
twisted qubits. Now, final thing is the theorem of Kontsevich, Manning, and also Ruantian, and it says all genus zero Gromov-Witten invariants for P1 can be computed recursively. Yeah, that's where it's also enters into play this topological recursion, because now given one, the first one, this given one initial value, then you can calculate the others from recursion relation. There is an expression how to calculate that, but I'm not going to say it. I'm just going to say that things, if you find one, then you can calculate the others. And this is that theorem is well established. You can check it by yourself. Okay. Once again, I want to show you the reference and then tell you that if you are a mathematician, maybe you should check this. If you want to understand just the physics, and also, I mean, math is also really nice here, but maybe it's more detailed in the physics side, you can check here. If you want to listen to some really nice lectures on the topic, you can listen to Chesmani. He has talked the same thing that I have mentioned here today, but in great detail. And then you can, if you want, curious about stable maps and moduli space, there is also quantum cohomology that I didn't have time to go on, but it's a way to generalize this from Witten theory, and also you have to check the gravitational descendants. And if you want something introductory just to read, if you are bored, then you can check this Sheldon Katz, Enumerative Geometry and String Theory. So with this, I will finish my